All right, so we've done some simulations where you looked at behavior of gas particles and looked at changing the pressure, the temperature, the volume, and you also watched some videos about those things. So we're going to do some gas law problems now, and so we can actually calculate the exact value for a gas of its volume, its temperature, its pressure. So just a little bit about pressure. Say you're standing at the beach. So here's this little person at the beach. The beach is 0 feet altitude. So if you go, because you're standing right at sea level. If you're at Bok Tower, that's about 100 feet above sea level. Mountain ranges are, of course, much higher. And so this person is standing at 0 feet. So he's at sea level. Here's the top of the atmosphere. And there is a column of air pushing down on this person's head. That's called air pressure. And so air pressure, normal air pressure at sea level is 14 pounds per square inch. So this person on the top of his head, every little square inch has 14 more pounds of pressure pushing down on his head. We don't really feel that because you've known it all your life. But if you're at the top of a mountain range, that person is closer to the top of the atmosphere, so there would be a lower pressure. So that pressure is going to be lower than you would feel at sea level. In a balloon, say this is a helium balloon, the helium particles are bouncing all over with all the kinetic energy that they have. And so those gas particles, as they bounce around, are hitting the inside of the balloon, which will keep it inflated. But the problem is that there's also air pressure. So air pressure is pushing in. So for the balloon to stay inflated, the helium pushing out, hitting the inside of the balloon, has to be a little higher pressure than the air pressure pushing in. If it wasn't, then the air pressure would just squish it flat. So there are a couple ways that we talk about pressure. One unit we use is called atmospheres, or ATM for short. If you're at sea level and you're feeling that 14 pounds per square inch, that's what 1 atmosphere is. So 1 atmosphere of pressure is exactly what you would feel at sea level on a clear day. Clear day matters because when it's going to rain, some of the air is pulled out into the storm so that the pressure drops. And then as the storm comes back in, it sort of increases. So when it's going to rain, you'll hear the weatherman say the air pressure is dropping, and that's because the storm is coming in. But on a clear day at sea level, 1 atmosphere of pressure is what the person would be feeling standing there at the beach. Another unit we use is called millimeters of mercury. Hg, remember, is the symbol for mercury, and we'll see why we call that millimeters of mercury. So you watched a video about Torricelli, who invented one of the first barometers, and wanted to measure air pressure. And so the way he did that was he took this glass tube, created a vacuum, took all the air out, and then had this pool of mercury. And he just turned the tube over, stuck it down in the mercury, and mercury gets pulled up to kind of fill that vacuum somewhat based on the air pressure. The air pressure is pushing down on this pool of mercury, and when it does that, it's going to push the mercury up into the tube. And so the way you figure out air pressure is you just measure from here to here, and that distance in millimeters of mercury is what the air pressure is. If it was a higher pressure day, there'd be more pressure pushing down on the pool of mercury, and the mercury would move farther up in the tube, and so this height would be a bigger amount. So it's just measuring the pressure of the air hitting that pool of mercury. So our pressure units, as we said, are millimeters of mercury, or ATMs, atmospheres of pressure. And so there is a set pressure that we use a lot in gas laws, and they just call it standard pressure. It's a very common one. It's 760 millimeters of pressure. Another way of saying that is 1 atmosphere, 1 ATM of pressure. Those are equal units, and they just come up a lot because if you're at the beach on a clear day, it's not going to rain, and you're at sea level, this is the pressure you would feel most likely. So we're going to work on something called Boyle's law. Boyle was a scientist who looked at how volume and pressure impact each other. So if you were to increase pressure, so the arrows here, so say you have a balloon and you take the outside and you squeeze on it, you squish on it, you can actually squeeze that volume into a lower, smaller volume because gas particles are so separated that you can take that balloon, squeeze it together, and end up with a smaller volume. So volume and pressure are opposite of each other. If you increase the pressure, the volume gets squeezed into a smaller space. The opposite would be true if I were to decrease the pressure. Say I had that balloon already squeezed into a smaller space and I let go of it, the volume is just going to re-expand. The particles are going to start to hit the inside of the container, and you're going to see that reinflation of the balloon. So volume and pressure always are opposite of each other. And so Boyle came up with a law to try and show that, so you can actually calculate how much lower or bigger the volume is. And this is Boyle's law. So it's V1 times P1 equals V2 times P2. So we're multiplying those. So V1 is the initial volume, P1 is the initial pressure of that balloon, and then you're going to do something to it. You're either going to squeeze on it or let up on it, and we're going to have a new volume, V2, and a new pressure, P2. So the 1s are your initial values, and the 2s are your final values. So here's an example over here on the right-hand side. Our starting volume is 20 mils, and we have a certain pressure. So let's say it's standard pressure. So we're going to use that 760 millimeter pressure that's called standard pressure. That comes up a lot. We want to increase the volume from the original volume to the final volume, the V2. So V1 is the initial volume, V2 is the final. It's going to go up 5 mils. So the volume is increasing. So we're going to increase volume in this problem. And because we know that V and P are opposites, if we increase volume, if the volume is going to expand, the pressure squeezing on the outside of that balloon would have to decrease a bit so that the volume could expand. So we would expect that this P2 down here that we're going to solve for would be less than 760 millimeters because we want the volume to go down. So we would plug in our numbers just into this equation here, Boyle's law. We would have P1 is 20 mils. P1, the original pressure, is 760 millimeters, 3 significant digits. We know the final volume is bigger, 25 mils, and we want to solve for P2. So if we want to solve for P2, we need to get P2 equals and have everything else on the other side. So we're just going to divide both sides by 25 mils. And of course you want to show the plug-in in, you want to show the work like we always do. So this cancels. When you're looking at the units, now we have P2 equals, and we're just going to do the math on this side. So just do the math, 20 times 760 divided by 25. And the least number of significant digits is actually 1. The 20 with no bar over the 0 is a 1 significant digit. And I got 608 when I did the math. So we're just going to drop that down to 600 so that we have just 1 significant digit. So we're still looking at significant digits, all the ones that are in our list of variables there. And then the units, we have a milliliter on the top and a mil on the bottom. So millimeters is our final unit. And that's what pressure should be in, millimeters. So we said that as the pressure went from, the volume went from 20 to 25 mils, volume got higher, the pressure should drop. And it did. It went from 760 to 600 millimeters. So from the original pressure, P1, to the final pressure, P2, the pressure dropped. So let's do another problem. We are going to look at with the volume and pressure in this one because you can see milliliters and millimeters. Usually you're given the initial values first. So we have a balloon that oxygen that has 150 mil volume, and the pressure, the push on the outside, squeeze on the balloon from the air pressure is 720 millimeters. So we're going to make our list of Boyle's law variables. And so the original volume of the gas is 150 milliliters. That dot behind the 0 is significant. So we're going to put a bar over it. And then the pressure originally on the outside of this balloon, the squeeze on this balloon, is 720 millimeters. We want to figure out how many milliliters, that means we're solving for volume, when the pressure is 750 millimeters. So would they say how many milliliters, you're solving for volume. If they said what would be the pressure, in terms of millimeters, then you would solve for P2. So looking at what changed, the P is changing. Pressure went from 720 to 750, so the pressure is going up. And we said V and P are always the opposite. If you squeeze more on the outside of the balloon, you're going to squish it into a smaller space. So if pressure goes up, volume goes down. So we would expect V2 to be something less than that 150 milliliters of V1. So we would expect V2 to be a smaller number. So we're going to use Boyle's law. V1 times P1 equals V2 times P2. So V1 150 milliliters times P1, 720 millimeters. We're solving for V2. And then the final pressure is 750 millimeters. Okay, so to solve, we want to get rid of the 750 millimeters on the right side. So we're just going to divide. So the 750 millimeters cancels. So we have V2 equals, and now you're just going to do the math on the left there. All the numbers had 3 significant digits, so you're going to want to work with 3 significant digits and to finish with. Millimeters are going to cancel, and so your volume would be, to 3 significants, 144. That would be your final answer. And so we said as the pressure went up from 720 to 750, that initial volume, that V1 here, ought to drop. And it did. It went when the pressure went up a little bit, so that it squeezes the balloon into a smaller space, so the volume goes down a little bit. If the pressure went up a lot, the volume will go down a lot. So it's inversely proportional. Okay. When you finish with doing the problems, take a look at Marie and Pierre. Marie Curie was the one that developed like ideas about radiation, and her husband Pierre. And so the scientist is using bunnies, they're peeps, marshmallow peeps, and we'll see what happens when he puts them in a vacuum pump, and it kind of shows some of the properties of gas laws. You'll work this problem the same way. Notice the pressure is not given in terms of millimeters of pressure, it's given in terms of ATMs. But you can plug in ATMs and solve for P2 and ATMs. It's just another pressure unit that you can work with. You do not have to convert it to millimeters. So if you'll just open the Boyle's Law problems that you see right below this video, you can work on those and see what answers you get. Just take the same steps that we just talked about. And text or call if you have any, or email if you have any questions.